So I've asked Ms. Burnham to give me a few problems to consider, and I'm not going to obviously do all of these in a video, but I think you've already talked about asymptotes. We'll have a little reminder and then how to tell the difference between an asymptote and a hole, just in case you've forgotten. I think you know, oh, I was showing Mr. Weiser how to use the screen and I kind of signed my name. Okay, so I think you know that with asymptotes you end up with these vertical lines, and horizontal asymptotes can be crossed as long as you approach them eventually. A vertical one cannot, because you have to get arbitrarily close to it and you want it to still be a function, so you just end up failing the vertical line test. But you might have something that goes like this over here, and then like that over there, and like that over there, and then it just kind of goes forever. So if you talk about it as a limit, as I'm going this direction, I would say that my limit is negative infinity, because I'm just going forever down. So I said something crazy, so I've gone back and I erased and now I kind of redrew this. But anyway, I'm going to write something that's not true about anything here. Or let me make it true. I'm going to change that. Okay, so I'm going to say this is A. So if I say the limit as x approaches A is infinity, that means it goes up forever. So what that means is, however big a number you think you can come up with, that it's going to eventually get bigger than that around in this area. So this is sort of similar to the limits where we're approaching a number, except you can't get within epsilon of infinity. So the way you get close to infinity is by being as big as I want. So this means for any number you pick, so that's a number, n, for all n, there exists a delta, so that when x minus a is less than delta, so x is arbitrarily close to a, f of x is bigger than n. So I'm just getting bigger than any number you want rather than getting closer to a limit. What it looks like is they're both approaching the same direction on the asymptote. Okay, so like over here, if I came from this side, it's going down forever, it's negative infinity. From this side, it's up forever, that's positive infinity. I don't know if you've already talked about, for a limit to exist, this requires that the limit from the left be the same as the limit from the right, BL. So from both directions, if I come from one direction close to there and one over there, then the limit does not exist because they're not the same. Okay, so the first years keep coming through here and messing me up. But so I was talking about left-sided and right-sided limits. So the same is true for infinite limits. If you're, so the picture I had drawn before where we had some, like over here, this one was going like this. Because it's positive infinity on this side and negative infinity on this side, then the limit doesn't exist, but you can talk about the individual sides. So let me get a couple of these. I'm just going to remember that was a 3. So the first question is, where do you have an asymptote? The thing that you have to do first is find out where your domain issues are. So you would check the denominator, which means I need to factor it. So then my domain issues are at x equals -2 and x equals 1. because there's no way to cancel that out so that either one of them is gone because they stay in the most simplified version, these are both asymptotes. So if I were graphing this, I'd have an asymptote at x equal -2 and an asymptote at x equal 1. And then I'd have to figure out what was going on in the middle, what was going on over here, what was going on over here. Probably want a horizontal asymptote calculation before you started doing that. Okay, on the other one, got more factoring to do. So on the top, I would first probably factor out a 4. And down here, I start out trying to factor by grouping because this is 4 pieces. So out of the first 2, I can get an x cubed. And then this one I need to take out a minus, and I take out a 9 and x. So I have up here x plus 3, x minus 2. Down here, x minus 2. Factor that out, I get x cubed minus 9x. So x minus 2. X squared minus 9. I'm going to just okay, I'm totally factored. So now I can say that x equals 2, x equals 0, x equals 3, and -3 are domain issues. Which is to say x can't be any of those things. But I can cross that out and cross that out so that I have holes at x equal 2 and -3 because it's like a factor of 1 coming out of there. So everywhere except 2, then I can cross this out because you can't cross out 0 over 0. So at 2, that's not true. Everywhere else I can cancel it out. Same thing with x plus 3. So those are holes. Asymptotes at x equals 0 and 3. So again, if you can factor it and cancel out so that if the 0 exists on the top and the bottom, then if once you cancel it out it's no longer in the bottom, because that could be there twice and still be there, then in that case it's a hole. If you can't cancel it out at all, it's not a 0 in the top, then it's an asymptote. Okay, so then let's look at these one-sided limits. I think that one says from the right. So the limit as x goes to -1 from the right. Of course, you'd first try plugging it in. You plug it in, you get 1 over 0, and that's bad. But as x gets close to -1, this is getting tiny, tiny, tiny. So you're getting 1 divided by tiny, tiny, tiny things, and there's a bunch of tiny, tiny, tiny things in 1. So you end up going towards some kind of infinity, and the question is it positive or negative? So as I'm coming from -2 to -1 from the right, you can just think, okay, so it's bigger than -1. So if x is bigger than -1, then x plus 1 is bigger than negative 1 plus 1, so it's bigger than 0. So it's positive, so you could say positive infinity. You can also kind of list some numbers out in a table. So this is x, and it's coming from the right, so maybe it starts out at 0, and then maybe it goes negative 1/2, negative 2/3, negative 4/5. Okay? So then, at 0, f is 1, 1 over 0 plus 1. 1 over 1 minus 1/2 is 2, because it's 1 over 1/2. 1 over 1 minus 2/3 is 1 over 1/3 is 3. 1 over 1 minus 4/5 is 1 over 1/5 is 5. So you can see that these are increasing. And if I kept getting closer and closer to negative 1, these would keep increasing, so it's infinite. Okay, the next one, x over x minus 2, I think that's also from the right. So if I just plug it in, I get 2 over 0, bad for the same reason. So if I'm coming from the right, then x is bigger than 2. This is positive. This time I have to consider this one, but if it's getting close to 2, then eventually it gets positive. So I've got positive up here, positive down there. So it's infinite again, infinite, positive infinity. I get close to 2 from the right, so 3, 2.5, 2.1, 2.01. So I have 3 over 1, 2.5 over 0.5, 2.1 over 0.1, 2.01 over 0.01. So that's getting bigger. Infinite limit again. I don't know why I keep pressing that button instead of the erase. Okay, this one, going to negative 3 from the left. Okay, so the one when I plugged in before, I got 1 over 0, and I got 2 over 0. This time, I'm going to get 0 over 0, which means I need to reduce first, because it might solve my problem by itself. So if it's not negative 3, then that cancels. So you actually don't have to do, this is not an infinite limit, this is just a hole in the graph. You do have an asymptote here at x minus 2, but we're not considering that. So I don't know that there's anything more to be done before you maybe try considering some. Yeah, some of these just plug in. Okay, so I will let Miss Burnham get back to me and let me know if there's anything more that needs to be talked about, and I'll talk to you next time.